finally, I think. All right, let me check to make sure. Good grief. Okay, so now on my end, this is static, right? In this static, this is static, right? Oh, there it is. All right. Golly. It's been one of those days. All right, so let me head into the book. Will realign us where we are. I'll tell you what, see if that helps a little bit. Okay. Don't worry, I got the wrong. That's it right there. All right. So, sorry for the delay there, but okay, so last time, or I don't know whether it was last time, but anyway, the last time we didn't have snow, what we were working on is dot products. And let's see, let me find a good problem to just work. Did I work? I think I worked this one at one point. But I'd like to find, there was a new one right there. Okay, determine the magnitude of a projected component acting along the cable AC. Let's just, okay, determine the angles. This is one that has 3 problems with it, so let's just do it. And what I'll do is I'll try to get the picture over here, and at the same time I'll get the different writings of what each one is. Uh-oh, I guess I'm just going to have to do a new page. Okay, so there's the problem itself, and this one has several questions about it. So what I'm going to do, I'm going to go grab them and list them down the right side. I think I'm going to try to work each one of them. Head off here and maybe put it over here or something. Alright, so now I can just work on this. Okay, so first thing he says is determine the angles between AB and AC. Second thing he says, determine the magnitude of the projected force component of that force acting on the cable, and then he wants to know the acting on the other cable. So first thing I'm going to have to do is find some vectors here. So luckily he gave us our coordinate system. If he didn't, we could use, our own choices to find that. So what I'm going to do is I'm going to try to find the vector. I'll start with this one. And I'm going to try this running down the coordinates first. So the first coordinate I'll run down is x. Okay. So if I'm running down x, I run to right there. And then if I'm going to run down y next, which that's totally legit, I run that way. And then I turn and run the z. So if you stare at that for a minute, you can basically find the vector that goes from A to B, and we'll need to do this again on C. And it looks like I do 6 here, And then it looks like I do 1 right here, but I'm going in the other direction. So I really need to, let me back up and put this. So I'm running back up the I direction. So this is the positive X direction. So I'm running the reverse direction to get from A to B. And then I'm running the reverse direction of J, which I only run 1 there. And then I'll run in the positive direction. This is going in the positive direction 2 to get to here. Now I hope that makes sense. If it doesn't, it's recorded. You can run it backwards here. But what I'm doing is a little bit different than what I did before, because I'm doing them in segments where I run the X and run the Y and run the Z. So now that I've done that for this vector, now I need to run that for the other vector. So the other vector is right here. That's R from A going to C. And again, I still go this 6 right here. So I go minus 6I. But then I go out the Y by a distance of 1. And then I go up. This time I go up 3 instead of 2. Now, my next goal is the unit vector in those particular directions. And on that, let me... Okay, wait. Hit the start. O-C-T-A. Okay, here we go. So I'm going to have to lay the keyboard in such a way that I can hit it. Okay. So, well, let's let it come up. I think I hit it. Okay, there it is. Okay, so I'm going to do a clear just to get rid of things, and CLC. Then what I'm going to do is I'm going to put RAB in there first. RAB is a vector that is minus 6, and then a minus 1, and then a plus 2. So I'll just work in the RAB, and then I'll work in the other one. So the norm, or the length, or the square root of the squares of RAB, let me guess, is it going to be, oh, it's not going to be an integer. Okay. So in Octave, when I type in the norm of, this RAB, what it's doing is it's taking the square root of the 6 squared, the 1 squared, and the 2 squared. And that's from the components here. And I'm going to go back to it becomes 6.4031, I think. Yeah. So that's the length of that vector. So you know what I'm going to do? Here's what I'm going to do for a moment. I'm going to kind of get this one. We figured it out, but I'm going to do it over here underneath this one. So that way we'll focus ourselves right here. So the unit vector going from A, so I'm working here right now. So I want to know what the unit vector is that goes from A to B, and it's minus 6I, minus 1J plus 2K, all that, over the 6.4031. So I'll just call it UAB is equal to RAB divided by the norm of RA and B. What happened here? Okay. Try that again. AB is equal to RAB divided by the norm that time it got tight. Okay. Okay, minus 0.937. Okay. Is equal to minus 0.93704. 93704 I. Minus 0.156 17J, and then plus 0.31235K. Now that's my unit vector, and I'm going to sort of hold on to that for a minute because I'm going to use it. And I'll show you how I'm going to use it. There's two ways I can solve this problem, but I'm going to do it by tracing down the unit vectors. So I'm over here now. So I'm done with that one for the moment. I'll just hold that one for a minute, and I'll go back in here and say, well, I want to know the unit vector going from A to C here. So minus 6I plus 1J. This time plus 3K, all over the square root of 6 squared plus 1 squared plus 3 squared, but that in Octave or MATLAB is just the norm of the vector. So I need to put the vector in there. That would be RAC, and it's still going to be the minus 6. It's going to be the 1 plus 1, and then is it 3? Yeah, 3. And then 3. So there's my vector, where the x is the first one, the y is the second one, and the z is the third one there. And so I got it listed in there, so now I'm just going to find the unit vector going from A to C there. We go to RAC, yeah, divided by the norm of RAC. Okay, so I'm going to bounce back and forth again. Okay, 0.88465I plus 0.14744J plus 0.44233K. Now, here's the deal. Okay, let's look in theory at something. You have any two vectors, and we can look back in the book and see this. So if you have any two vectors, A and B, the two vectors will make up a plane somehow. You know, you could have two vectors pointing in two different directions. There's going to be an angle between them. So if you dot the two, and you look back in the text, it's nothing more than the magnitude of the first one, the magnitude of the second one, times the cosine of the angle between them. So this is kind of a given. But also, if you look at the left side, what you find out here, of course, and we're going to basically do it so that we don't even have to do this, but if you look at it, a dot product becomes a scalar, or just a number, and its value becomes this. Oh, that's not A, that's a B. So that's its value. So now if I use this thought process and I say to myself, okay, I'm going to use this one for A maybe, and this one for B. The first thing is they're unit vectors. So their magnitudes are just going to be 1 and 1. So I can sit here and dot this. In other words, Okay, so I'm going to dot it on the page, and then I'm going to go to MATLAB and let it dot it. So if I'm going to say UAC, which is that one, dotted with UAB, which is that one, then what I'm going to do, I'm going to grab the X component first. So I'm not going to multiply them out, but I'm going to write them. Minus 0.88465 times the X component here, minus 0.93704, plus, now I'm going to go to the Y component. Here's your Y component, 0.14744, that one's from there, and then this one comes from up here, minus 0.15617. And then I got one more to do, and that's the, that's the Z component. So here's your Z, 0.44, and I hope I'm copying these down right. That times the one over here, 0.31235. Okay, so I can go ahead and multiply those out, but what's interesting is inside octave, he's got this thing called a dot. So if I dot two vectors, and I just happen to dot UAC with UAB, that number that pops out of there, oh, well, yeah, if you dot a vector against itself, it becomes 1 because that gives you the length. We made the unit vector 1, but I mistyped that, so that should say AC, right? Okay. Sorry about that. So I mistyped this first one. Since I made these unit vectors, then essentially if you dot a vector against itself, its length over here is 1, and its angle would be 0, which gives you back a number 1. So it makes sense that that's what I got there. However, I didn't get that when I did AB dotted with AC. So I get 0.94409. Dotted with B. Now, turns out if I look at the right side of this equation, I get this. Okay, so what I'm doing is I'm grabbing this side now, and instead of A and B, I've got UAC, the magnitude of it, UAB, the magnitude of it, and the cosine of the angle between them. Well, we've made this so this is, 1. And we made this so it's length 1. So all I have now is cosine, let me write this down, is this. So from that, I can go into MATLAB, not CAS, COS, inverse of 0.94409 equal to, now, I wonder if I can just do this, do arc cosine. I want the answer in degrees. And then what I want to do is close the bracket. So 19.25. So the theta is equal to 19.25 degrees. If I didn't do the D at the end, it would have become radians. So, not a bad issue, I guess. I don't know. So the question is, okay, that's 222 right there. So I want to spin around and find the answer, and maybe it's possible. Pushed the wrong thing. Why did I do that? Okay, wait. Okay, give me a second. That's, statics appendix. Okay, 122. starting in the F, so that's past that. 2, what? Oh, these are preliminary problems. Okay. That's something that's new in this edition. Here's the, no, that. Okay, now they got review problems. Where's the real problem? They all have an R in front. So now they have a P. Okay, here we go. 122. So if you look, I don't think I can select these, but I can do that. So there's the 122. So now, let's look back. I'm sorry, 19.2. Let's look back. Well, I carried an extra. And see what else he wanted to find. And what he wanted to find next, he didn't mention this force before, but now he's just mentioning it. And he says, I want to find it acting along the cable BA. And BA would be this cable right here, you know, from this end to this. So luckily, we went ahead and found this thing. So, and that's AB. Okay, so let's go over here, and here's what we'll do. We'll kind of isolate ourselves away and say we're solving 122-123. So he says our force is equal to 400 I minus 200 J plus 500 K, I think. Yeah. Now, if I dot this thing with some sort of vector that this thing has a unit, it's a unit vector, then I'll actually find, okay, so let me give you an example. So here's F. I have some weird direction here, U, and what I want to do, let me lean U a little further over. So let's say U is this way. So here's your U vector. Well, what you're trying to do is you're trying to come up with that. The component of F in that direction. Well, if this is the angle between it, and that's the unit vector, lo and behold, that's nothing more than here. That length is nothing more than the length of F times cosine of, theta. Let's say, what did I say that? That's theta. So, in essence, you take the dot product. Because, here's the deal. If you look back here at this, and you say, oh, I'm just going to make this so that B becomes a unit vector. And A just happens to be the force. Sorry for the delay there. Then this is the right-hand side is what you're looking for. Now, you got two choices here. Well, no, you have one at this point. The easiest one is just take the dot product. And that dot product will give you that value going along this direction here. So let me just do that, and I'll just borrow MATLAB to do it, or Octave here. Since I already have U, so he wanted to know this is AB. So he wanted to know that. So what I'm going to do is 400. I'm going to do it in longhand a little bit. 400 K dotted with, okay, so now we'll just copy this across. 0.93704 I 0.1560 no, 17J plus 0.31235K, and you dot those. Now you can do this a couple ways. One, multiply times that and that. Add these two together and add these three. So you multiply these and then add them all together. So in other words, it'd be 400 times the minus 0.937 plus a minus 200 times a minus 0.156, and then plus a 500 times a 0.312, and that'd give you a number. Now, the beauty is, if I go to octave, which is not there, it's right there, and then let's get that back in sequence so I can go back and forth. I already have U, I have both U's, I just don't have the F in there yet. So I'll put the force vectors in there, and luckily I don't think he changes it between the two problems. So it's a 400, and then it's a minus 200, and then it's a 500, and then it's gone. No, I mean it's there, but yeah. So what I'm going to do is dot the force vector with UAB. I did type that right. Now, here's the deal. Is it a minus sign or is it a plus sign? Here's what's funny. I can flip this, I'll get the same sign. I'll get the same thing. So in other words, I can do this. And guess what? I get the same thing. Now, the sign, what does the sign mean? Let's take a look back at the picture and zoom in on it. Now, this is not really that good, but as far as a picture goes, but this is pulling away, and my vector is going this direction. So if it was positive, that means it would be going this direction. Since it's negative, that means it's going that way. And so it's not a big deal. And now I've already forgot its value. And I forgot where I had it. Here it is. So the vector component of F going along AB, the magnitude of it is, I think it was 187.4. And so that's the magnitude. Now, which direction it goes, that's kind of, so there's your 187. And then I had a 0.4. Now, he was saying going from B to A. So technically, if you really want to be precise, that vector that I drew, so I had, this vector is U, A, B. However, if you want to know the direction here, it's U, B to A. Each one of these is minus the other, and if they're all unit length, they're exactly opposite. So that's why I get a minus, and he does not. Now see, he says along the cable C to A, and of course, what did I do? I did the same thing I did on the other one, which it's okay. I basically pointed this way, U, A to C. He wants it to be this direction, so he's saying U, C, C to A. So when I dot mine, I'm going to get the minus of what he had. So it's okay. So now, how do you do that? Well, you do the same way again. You do F dotted with U. Okay, so I have AC. He wanted C to A. So in short, I'll just go over to the wrong place. I'll go there, and there, and back. Now, I got F in there already, so now I'm just going to do a dot, F, U, A to C. And I get 162.19. Again, he wants it in the opposite direction. So he should have plus 162, roughly. I don't know. Uh-oh. Oh, wait a minute. No, wait a minute. There isn't. Wait a minute. There's 123. Where's 124? Did I miss something? Okay, let me go back. Is this a situation where they... This is probably a situation... Oh, yeah. Okay. I think that asterisk means there's no answer in the back of the book. I think that's what that means. So I had 124. There's no answer there. So it should go right here, but I don't have it. But the technique is exactly the same. So let's head back in and 222 right there. It's a little slow today, and it's running hot. So essentially, dot products, that's all you're doing, is you're basically, if you really look at it, you're doing something very simple. You're basically finding a direction, putting a unit vector, then dotting it with the force. Okay. Actually, that's probably more suited for a later chapter right there, because that could be talked about differently. The rest of them, let's see. Determine the length of the chain expressed with the acting along the chain. Cartesian, determine its coordinate direction angle. So he wants to know the force acting along the chain. He already gives you 50 pounds. So there's no dot product there. So I think next time what I'll do is tackle or make sure we go through the homework that I've assigned. But for the next few minutes, I think I'm going to go into this cross product thing, which I'm wondering if that's a new chapter. I think it's a new chapter. Yeah. So that being a new chapter, let's see if I've got 3 sitting somewhere. There it is. And the reason it's good to do it right now, and I'm way up at the, okay, way up here. Is really because you already have this as a feeling, so to speak. For example, if you had a chain that sat here, and you had an X coordinate and a Y coordinate, and then you had the tensions here, and then you had the weight, you would know that the component in the Y direction of these two tensions offset that weight, or else it's going to fall or be pulled up. So what he's saying here is, in statics, sum of the forces equal mass times acceleration, but we don't have any acceleration because it's static, and so we get that. And then there's a vector equation, so like we talked about before, the dark kind of indicates that it's a vector. I can't do that, so I have to put an arrowhead over the top of mine. So you already know this, or you already probably got a feel for this. Maybe. And then if you just roll down through here, okay, then this is something that really is kind of annoying to me, but it's okay. He puts in here this spring. Well, the reason he's tossing it in there, he may give you something in which the thing deflected. And then if it deflected, here's your deflection. And you give him the spring stiffness, you can just find the force. That's all he's doing. This really isn't critical to the understanding of what's going on here. You already know it, but okay, cables and pulleys and smooth contacts, that's kind of convenient. And I don't know, does he have oh, here we go. So if you've got a frictionless pulley, whatever tension's here is going to be the same tension here. And the way you can do that is if you look at the pulley itself, then I don't know that that's a great drawing. But if you sum the moments, oh, we hadn't done sum the moments yet. Anyway, well, in any case, if this thing is sitting and not twisting, then this torque from this distance has to equal to that one. Later on, we'll talk about the moments. So you got cables, pulleys, smooth contact, which basically that's saying, you know, okay, you got a wall right here. This thing is just making a force go back up. He always calls it N. I always call it the nothing force, because it really doesn't do nothing, but it keeps it from crashing through here. That's about all it does. So it has to be included in the sum of the forces. So in other words, at this particular point, you'd have to choose, okay? I can maybe make the x coordinate go this way, or maybe I want it to go, maybe I'd like it to go this way. And then what you would do is you would sum the forces in the x direction equals 0, and you'd add them up, which would be the component going here, you got a y here, and you got the component going here, and then you got the y here. It turns out, if you really look at this length of vector is supposed to be exactly the same as that length for this to hold. The normal force, or the do-nothing force, pushes to the left, and the tension is pulling slightly to the right at 20 degrees or whatever. And so that gives you the relationship to N to T, and then you got to wait, and then you do the sum of the forces in the Y equals 0. And that'll be this component, and this. And you can solve all that. And so we'll do that. I got 5 more minutes, but and that's it. Now, the other thing he talks about, he talks about something called a free body diagram, and I don't know. Let's see. Where is he actually? He's not talking about it yet. Okay, now he's talking about coplanar forces, the X and Y. Nothing new there. So come into focus. Okay, free body diagram. He talks a second about it, but what that is essentially erasing the body and replacing it with the forces. So if you have something like this, you would erase the structure and you would replace it with the tension. That's all he's basically saying. Tension BC, tension BA, I think. And so that's what the free body is. And so, and that's what he does right here. He basically puts those together, sums the forces in the X and Y, and comes up with a solution. Now, I think this is a different problem down here, because he stops and says answer. Okay, so this must be the end of that problem. And it's a very strange thing, because, okay, here he says, here's an example with a blue ribbon there. And he doesn't have a blue ribbon right here. And then he just starts working another problem. And he says that's 3, 4. So we went from 3, 2. So that, maybe there's a problem with the text. Maybe that blue ribbon's supposed to say there 3.2 or 3.3. So what we'll do, these are kind of cool problems here. We'll come back and do some of these. We got 3 minutes left. Yeah, these are quite fun and interesting, and there's some stuff that can come out of these. There's your springs, which those are, to me, they're just annoyances, but we'll deal with it. So maybe we'll work this problem next time. So I don't know. Sorry I got started late, but this morning I had to cancel the class because I couldn't even log into the system. So at least we got logged in. Oh, and I didn't do the word of the day. Oh shoot, let's do that real quick here, because people are here, so we might as well get some extra credit. Okay, come on, here we go. That is, let's not assume I can log into this either. I mean, I had problems before, just a couple hours ago. Let's see. Logging you in. Oh, okay. Wow, that's different. Okay, I got a cell phone that tells me the word of the day. Let me see. Let me find it. Oh, here, I just look at this. There you go. Okay, so here's the course. It's spring. This is still statics, which for some reason they list at the bottom of all this. Don't know why. Okay, now I'm going to, instead of going to content, I'll go to the attendance module, which I thought I reset that, but okay. There's my email, and we'll use the word connect. Okay, hit the button there, go. All right, so throw that in when you can, and we'll call it good. So I'll go ahead and drop the stream.